Good afternoon, everybody. This is just a quick video showing you what is going on with the PDF that I sent to you yesterday. So this is some information that we need to look at mixed random variables. It's typically it's sort of assumed that you know it at this point, but mainly it's something for you to read, but I am going to go quickly through it. So I start out by looking at definitions of functions. So we look at the average value of a function, which is all standard stuff. We look at the derivation of the integral version of it and come up with the standard definition. Then I go on to talk about average energy for a particle executing simple harmonic motion. In this particular case, the average kinetic energy is actually zero. Sorry, the average energy is zero, but the average kinetic energy is not equal to zero. So if we apply the average value of a function expression, and I note that you can, to integrate over a period, you can go 0 to 2 pi or minus pi up to plus pi. Since it's simple harmonic motion, we use a sine or a cosine to describe it. So we've got to be able to average those functions. And what I do is I show you how to do the average of sine squared, the average of cosine squared, and basically through all of that, give us a method for calculating average values of functions. The results should be well known to you. Then I review periodic integrals and state some results, which again are fairly straightforward. So, and through all of this, what we come up with is that for a periodic function, the integral over any period is equal to the integral over the principal period. And the principal period will typically take as zero, is that first interval from 0 to 2 pi, or maybe the one from minus pi up to plus pi. I then go on and introduce the step function, but to do that, I first show you how to define a generalized function. Generalized functions are functions that are similar to regular functions, but have some different properties. And the one we'll be most interested in is the delta function. But I start by introducing the unit step function because it's easier to see what's going on. And I basically point out that it's a function that's equal to 1 for at some time and values of time greater than it, and it's equal to 0 below that. We happen to pick t equals 0 at the time. So we can use this in our integral that describes generalized functions. And we can work things out and get a relationship, and essentially that allows us to calculate the expression for the unit step function. And then I point out you can determine the properties of other generalized functions in the same way. We're not going to. We're going to study the properties of the step function, but most other functions that you meet in applications can be treated in the same way. And so I review the definition. I point out that in the discontinuity, we can make different choices for what the value of the function is, and the choice that we make depends actually on the application. So in most cases, it's going to be convenient to take the value 1, and because of that, we rewrite the definition so that it starts from t equals 0. And this is just a way to show the discontinuity for that alternate definition. And then I introduce a step function with a shift in it. In other words, one that has the discontinuity at the point t equals a rather than the point t equals 0. And I go through an example there, introduce the function, and show you how you can sketch it. Then I introduce the idea of a rectangular pulse, and I'll show you how you can write that, and come up with an expression for it. Rectangular pulses are things that come up all the time. Then we actually get to the Dirac delta function, and I first talk about how we introduce it by considering an impulse, and talk about the analysis of that impulse using the impulse momentum theorem, and then introduce the Dirac delta function, and define what it is. So here's some pictures of it. And we talk about the requirements that we have for this so-called function, and we point out that it's not an ordinary function. And then I give you an exact definition for it. It's a function whose value is 0 at most points, and at a single point, in this case t equals 0, it has an infinite value, but it also has an integral over all space equal to 1. So then I apply a test function to it using the methods of generalized functions, and come up with some properties. And particularly we're interested in the sifting property. And what that means is that if you take a function that we might call a test function, multiply it by a delta function, integrate over space, it actually generates the value of the test function at a particular value of the argument, and in this case I chose 0 to be that value. And that's called the sifting property. Then I introduce the delayed delta function, much like a delayed step function. And then I state some properties of the delta function for you, and then note that you can use the delta function to express continuous time signals. And then I just introduce a couple of other signals for you. One is the unit rectangle, and the other is the unit ramp. And these are a couple of signals that appear many times in applications. So the main point here is to introduce the idea of a generalized function and the idea of the Dirac delta function. I will be making some use of them next week. And all I ask you to do is to read through the notes and grasp the major ideas, but it's the results that we're going to be most interested in. But if you read this set of notes thoroughly, you'll actually get a pretty good understanding of the delta function in terms of its definition through generalized functions. So I'll quit at this point.